Imagine this, a distant star, light years away, winking at us. Not because it's saying hello, but because a planet is passing in front of it, blocking a tiny fraction of its light. This isn't science fiction, it's how we've discovered thousands of exoplanets. But that's just one method. The universe is vast, and the tools we use to explore it are equally diverse. From the transit method that spotted that winking star to the intricate dance of microlensing. Each technique has its own story, its own strengths, and its own limitations. In this video, we're diving into the fascinating world of exoplanet detection. We'll explore real missions like NASA's Kepler and TESS, and we'll see how each method brings us one step closer to answering one of humanity's oldest questions. Are we alone in the universe? Stick around, because the methods we're about to discuss aren't just about finding planets. They're about finding our place in the cosmos. Overview of exoplanet detection methods. The quest to find exoplanets, or planets outside our solar system, has led to the development of several innovative detection methods. Each technique has its unique approach, advantages, and limitations. The transit method is one of the most prolific, involving the observation of a star's light dimming as a planet passes in front of it. This method is highly effective for detecting planets with short orbital periods and has been instrumental in the discoveries made by missions like NASA's Kepler and TESS. The primary advantage of the transit method is its ability to detect multiple planets around a single star and provide information about the planet's size and orbital period. However, it is limited by the need for a precise alignment between the planet, star, and observer, and it is less effective for detecting planets with large orbital periods or those that do not transit in front of their star from our perspective. Another powerful technique is the radial velocity method, also known as the Doppler method. This approach measures the tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. The high-accuracy radial velocity planet searcher, HARPS, spectrograph, for instance, has used this method to discover numerous exoplanets. The radial velocity method is particularly useful for detecting planets close to their stars and can provide information about the planet's mass and orbital period. Yet, it is less sensitive to smaller, Earth-like planets and can be affected by stellar activity, which can mimic the signals of planets. Direct imaging offers a more straightforward approach by capturing actual images of exoplanets. This method involves blocking out the light from the parent star to reveal the much fainter light from the planet. The Gemini Planet Imager and the Sphere instrument on the Very Large Telescope are examples of advanced technologies used in direct imaging. This technique is advantageous for studying the atmospheres and compositions of exoplanets and can detect planets at large distances from their stars. However, it is challenging due to the overwhelming brightness of the parent star and is currently limited to detecting young, massive planets. Gravitational microlensing is a fascinating method that relies on the gravitational field of a foreground star to magnify the light from a background star. When a planet orbits the foreground star, it can cause an additional brightening of the background star's light. This technique has been employed by missions like the Microlensing Observations in Astrophysics, MOA, and the Optical Gravitational Lensing Experiment, OGLE. Microlensing is particularly effective for detecting planets at large distances from their stars and can provide information about the planet's mass and orbital distance. Nevertheless, it is a rare and unpredictable event, making it less suitable for follow-up observations and detailed characterization of the detected planets. Historical context and evolution. The quest to detect exoplanets, worlds orbiting stars beyond our solar system, has been a thrilling journey marked by ingenuity and perseverance. Early efforts were hampered by technological limitations, but the field has since burgeoned into a vibrant area of astronomical research. The first exoplanet discovery around a sun-like star, 51 Pegasi b, in 1995, opened the floodgates. This breakthrough was achieved using the radial velocity method, which detects the tiny wobbles a planet induces in its host star's motion. The method remains popular today, with missions like the High-Accuracy Radial Velocity Planet Searcher, HARPS, spectrograph in Chile contributing significantly to the field. However, radial velocity has its limitations, such as a bias towards detecting large, close-in planets and difficulties with distant or faint stars. Transit photometry has emerged as another powerful tool in the exoplanet hunter's arsenal. This method involves measuring the tiny dip in a star's brightness as a planet passes in front of it. The Kepler Space Telescope, launched in 2009, is the poster child for this technique. It has discovered thousands of exoplanets, including many small, rocky worlds in the habitable zone. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018, is Kepler's successor, focusing on bright, nearby stars to facilitate follow-up observations. Despite its successes, transit photometry has its drawbacks. It requires precise alignment between the star, planet, and observer, and it struggles with identifying planetary properties like mass or composition directly. Direct imaging offers a more intuitive approach, capturing actual images of exoplanets. This method is particularly effective for young, massive planets orbiting far from their host stars. The Gemini Planet Imager, for instance, has directly imaged several exoplanets, providing valuable data on their atmospheres. However, direct imaging is technically challenging due to the overwhelming brightness of stars compared to their planets. It also favors young, massive planets, leaving many smaller, older worlds undetected. Moreover, it requires advanced adaptive optics and coronagraphs to block out starlight, making it less accessible than other methods. Gravitational microlensing is a more unconventional technique, relying on the bending of light by gravity to detect exoplanets. When a star passes in front of another star, its gravity can act like a lens, magnifying the light from the background star. If the foreground star has a planet, the planet's gravity can create a distinctive blip in the light curve. The microlensing observations in astrophysics, MOA, and optical gravitational lensing experiment, OGLE, collaborations have used this method to discover several exoplanets. Microlensing is sensitive to planets at large distances from their host stars and can detect low-mass planets. However, it is a one-time event, making follow-up observations challenging. Additionally, it requires precise alignment and is less suited for studying planetary systems in detail. Each method has its strengths and weaknesses, but together, they form a comprehensive toolkit for exploring the exoplanet frontier. Basic principles of exoplanet detection. Detecting exoplanets, or planets outside our solar system, relies on a variety of methods, each with its own principles, advantages, and limitations. The transit method is one of the most successful and widely used techniques. It operates on the principle that when a planet passes in front of its host star, it blocks a small amount of the star's light. This tiny dip in brightness can be detected by sensitive instruments. Missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, have used this method to discover thousands of exoplanets. The advantages of the transit method include its ability to detect small planets and provide information about their size and orbit. However, it has limitations. It only works if the planet's orbit is aligned just right for a transit to be seen from Earth. Additionally, it can be tricky to confirm the nature of the detected object, as other phenomena can cause similar dips in brightness. Another method is the radial velocity, or Doppler method. This technique detects the slight wobble in a star's motion caused by the gravitational pull of an orbiting planet. As the star moves toward and away from us, its light spectrum shifts slightly, a phenomenon known as the Doppler effect. Instruments like the High-Accuracy Radial Velocity Planet Searcher, HARPS, have been instrumental in this method's success. The radial velocity method is particularly good at detecting large planets close to their stars. It also provides information about the planet's mass and orbit. Yet, it has its challenges. It's less effective at detecting small, Earth-like planets, and it struggles with distant planets. Moreover, the method can be time-consuming and requires precise, long-term observations. Gravitational microlensing is a fascinating method that takes advantage of Einstein's theory of general relativity. When a star with a planet passes in front of another star, the gravity of the foreground star acts like a lens, magnifying the light from the background star. If the foreground star has a planet, the planet's gravity can cause a distinctive blip in the brightening. Missions like the Microlensing observations in astrophysics, MOA, and the optical gravitational lensing experiment, OGLE, have used this method. Microlensing can detect planets at large distances from their stars and can find low-mass planets. However, it's a rare and unpredictable event, making it difficult to study individual planets in detail. Additionally, microlensing events are usually one-time occurrences, so follow-up observations are limited. Direct imaging is a more recent and challenging method. It involves taking actual pictures of exoplanets. This is difficult because the light from the host star is much brighter than the planet. Advanced telescopes and instruments, like the Gemini Planet Imager and the Sphere instrument on the Very Large Telescope, use special techniques to block out the star's light and reveal the planet. Direct imaging can provide a wealth of information about a planet's atmosphere, composition, and even weather. It's particularly good at detecting young, hot planets that are far from their stars. However, it's limited by the brightness of the star and the distance of the planet from its star. It's also technically challenging and requires advanced technology. Each method has its strengths and weaknesses, and often, multiple methods are used together to confirm and study exoplanets. Transit method, fundamental concepts. The transit method is one of the most successful techniques for detecting exoplanets, responsible for the discovery of thousands of planets orbiting distant stars. At its core, this method relies on the observation of a star's light dimming as a planet passes in front of it, known as a transit. When this happens, the planet blocks a small fraction of the star's light, causing a tiny dip in brightness. Astronomers can detect this dip and infer the presence of a planet. The amount of light blocked provides information about the planet's size, while the frequency of the transits reveals the planet's orbital period. NASA's Kepler Space Telescope is a prime example of a mission that has utilized the transit method to great effect. Launched with the specific goal of finding Earth-sized planets in habitable zones, Kepler has identified over 600 confirmed exoplanets. The telescope continuously monitored the brightness of over 150 stars, looking for the characteristic dips in light caused by transiting planets. This method is particularly effective for detecting planets with short orbital periods, as they transit more frequently, making them easier to spot. However, it is less effective for planets with large orbital periods, as transits are rare and can be easily missed. One of the key advantages of the transit method is its ability to detect small, Earth-sized planets. By measuring the depth and shape of the transit light curve, astronomers can determine the planet's radius and even infer its atmospheric composition. This is done through a technique called transmission spectroscopy, where the light passing through the planet's atmosphere during a transit is analyzed. The transit method is also relatively straightforward and can be implemented with ground-based telescopes, making it accessible for many astronomers. Despite these advantages, the method has its limitations. It is biased towards detecting planets with orbits that are edge-on from our perspective, meaning it misses many planets with different orbital inclinations. Additionally, it is less effective for detecting planets around faint or distant stars, where the transit signal is too weak to be detected. Another limitation is the potential for false positives, where other phenomena, such as eclipsing binary stars, can mimic the transit signal. To mitigate this, astronomers often use follow-up observations with other methods, such as the radial velocity method, to confirm the presence of a planet. Despite these challenges, the transit method remains a powerful tool in the search for exoplanets. Ongoing missions like NASA's Transiting Exoplanet Survey Satellite, TESS, continue to build on Kepler's legacy, surveying the sky for transiting planets around the brightest stars in the sky. This method has not only expanded our understanding of planetary systems, but also paved the way for future missions aimed at characterizing the atmospheres of exoplanets and searching for signs of life. Transit method, light curve analysis. The transit method is one of the most prolific techniques for detecting exoplanets, responsible for the discovery of thousands of planets. It relies on the observation of a star's light curve, which is a graph of its brightness over time. When a planet passes in front of its host star from our perspective, it causes a tiny dip in the star's brightness. This dip is what astronomers look for, and the size and shape of the dip can reveal a lot about the planet. The process begins with continuous monitoring of a star's brightness. Missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, have been designed specifically for this purpose. They stare at a patch of the sky, measuring the brightness of thousands of stars simultaneously. When a transit occurs, the star's light curve shows a characteristic drop and then a return to normal. The depth of the dip depends on the size of the planet relative to the star. A larger planet will block more light, causing a more significant drop in brightness. The duration of the dip can also provide information about the planet's orbital period and distance from its star. One of the main advantages of the transit method is its ability to detect small, Earth-sized planets. It is also relatively straightforward and cost-effective, as it relies on measuring changes in brightness rather than direct imaging. However, there are limitations. The method is most effective for detecting planets that orbit close to their stars, as these have shorter orbital periods and thus transit more frequently. Additionally, it requires that the planet's orbit be aligned just right so that it passes in front of its star from our viewpoint. This means that many exoplanets may be missed if their orbits are not favorably aligned. Another limitation is that the transit method can only provide information about the planet's size and orbital period directly. To learn more about the planet's mass, density, and atmospheric composition, additional methods like radial velocity measurements or follow-up observations with other telescopes are needed. Despite these limitations, the transit method has been incredibly successful. Kepler, for example, has discovered over 600 confirmed exoplanets using this technique. TESS, which was launched in 2018, is expected to discover even more, focusing on bright, nearby stars that are well suited for follow-up observations. The data from these missions not only help astronomers identify new planets, but also provide valuable insights into planetary systems' formation and evolution. By analyzing the light curves, scientists can study the atmospheres of exoplanets, looking for signs of life or habitability. This method has truly revolutionized the field of exoplanet research, opening up new avenues for exploration and discovery. Transit method, advantages and limitations. The transit method is one of the most prolific techniques for detecting exoplanets, responsible for the discovery of thousands of planets. It operates on the principle of observing a star's light dimming as a planet passes in front of it, known as a transit. This method is particularly effective for detecting planets with short orbital periods, as they transit more frequently. The Kepler Space Telescope, launched by NASA, is a prime example of a mission that has utilized the transit method to great success. It has identified over 600 confirmed exoplanets by continuously monitoring the brightness of more than 150 stars. One of the key advantages of the transit method is its ability to detect small, Earth-sized planets. This is crucial for the search for potentially habitable worlds. Additionally, the transit method can provide information about the planet's size, orbit, and even the composition of its atmosphere through follow-up observations. The data obtained from transit events can be used to calculate the planet's radius and orbital period, offering insights into its potential habitability. Moreover, this method is relatively straightforward and cost-effective, making it accessible for both ground-based and space-based observatories. However, the transit method has its limitations. It is biased towards detecting planets with short orbital periods, as these transit more frequently and are easier to observe. This bias means that long-period planets, which might be more akin to those in our solar system, are less likely to be detected. Furthermore, the transit method requires the planet's orbit to be aligned edge-on with our line of sight, which is a relatively rare occurrence. This geometric constraint limits the number of stars around which transiting planets can be detected. Additionally, the method is less effective for detecting planets around faint or distant stars, as the transit signal becomes harder to discern. Another limitation is the potential for false positives, where other astrophysical phenomena, such as eclipsing binary stars, can mimic the transit signal. To mitigate this, follow-up observations using other methods, such as radial velocity measurements, are often necessary. Despite these limitations, the transit method remains a powerful tool in the exoplanet hunter's arsenal. Its strengths in detecting small, potentially habitable planets make it an invaluable part of the ongoing search for Earth-like worlds beyond our solar system. Radial velocity method, fundamental concepts. The radial velocity method, also known as the Doppler spectroscopy method, is a technique used to detect exoplanets by observing the gravitational influence they have on their host stars. This method relies on the fact that a planet's gravity causes its host star to wobble slightly as the planet orbits it. By measuring these tiny wobbles, astronomers can infer the presence of an exoplanet. The method is particularly effective for detecting large planets orbiting close to their stars, such as hot Jupiters. The radial velocity method is ground-based and has been instrumental in the discovery of many exoplanets, including 51 Pegasi b, the first confirmed exoplanet orbiting a Sun-like star. This method is also used by missions like the High-Accuracy Radial Velocity Planet Searcher (HARPS) spectrograph, which is part of the European Southern Observatory's ESO 3.6-meter telescope at La Silla Observatory in Chile. HARPS is renowned for its precision and has discovered numerous exoplanets, including some in the habitable zone of their stars. To detect exoplanets using the radial velocity method, astronomers first observe the spectrum of a star. They look for periodic shifts in the star's spectral lines, which are caused by the Doppler effect. As the star moves toward us, its spectral lines shift to shorter wavelengths, blue shift, and as it moves away, they shift to longer wavelengths, red shift. By measuring these shifts over time, astronomers can determine the star's radial velocity, the speed at which it is moving toward or away from us. The periodic nature of these shifts reveals the presence of an orbiting planet. The amplitude of the shifts indicates the planet's mass, while the period of the shifts reveals the planet's orbital period. This method is highly sensitive and can detect planets with masses as low as a few Earth masses. However, it is less effective for detecting planets with long orbital periods, as these require longer observation times to confirm. One of the main advantages of the radial velocity method is its ability to detect planets with a wide range of masses, from massive gas giants to smaller, rocky planets. It is also effective for detecting planets around stars of various types and ages. Additionally, the method can provide information about the planet's orbital eccentricity and the orientation of its orbit. However, the radial velocity method has some limitations. It is less effective for detecting planets with long orbital periods, as these require longer observation times to confirm. The method is also biased toward detecting planets with short orbital periods and high masses, as these produce larger radial velocity signals. Furthermore, the method is less effective for detecting planets around very active stars, as stellar activity can mimic the signals caused by planets. Despite these limitations, the radial velocity method remains a powerful tool for exoplanet detection and has contributed significantly to our understanding of planetary systems beyond our own. In practice, the radial velocity method involves precise measurements of a star's radial velocity over time. Astronomers use high-resolution spectrographs to measure the Doppler shifts in the star's spectral lines. These spectrographs are often mounted on large ground-based telescopes, such as the ESO's HARPS or the Keck Observatory's high-resolution Echelle spectrometer, HIRES. The data collected by these instruments are then analyzed to identify periodic signals that indicate the presence of an exoplanet. Advanced data analysis techniques, such as the use of Bayesian statistics, are often employed to distinguish between planetary signals and other sources of variability, such as stellar activity or instrumental noise. The radial velocity method is often used in conjunction with other detection methods, such as the transit method, to confirm the presence of exoplanets and to determine their properties. This multifaceted approach allows astronomers to gain a more comprehensive understanding of exoplanetary systems and their characteristics. Radial velocity method, spectroscopic analysis. The radial velocity method, also known as the spectroscopic method, is a technique used to detect exoplanets by observing the gravitational influence of an orbiting planet on its host star. This method relies on the Doppler effect, which causes the star's light spectrum to shift slightly as it moves toward or away from us. Astronomers measure these shifts to infer the presence of an unseen planet. The method is particularly effective for detecting large planets orbiting close to their stars, such as hot Jupiters. One of the earliest and most successful missions employing this method is the High-Accuracy Radial Velocity Planet Searcher, HARPS, spectrograph, mounted on the European Southern Observatory's 3.6-meter telescope at La Silla, Chile. HARPS has discovered numerous exoplanets, including some of the smallest known to date. The process begins with the collection of starlight using a high-resolution spectrograph. This instrument splits the light into its component wavelengths, creating a spectrum that can be analyzed for subtle shifts. When a planet orbits a star, its gravitational pull causes the star to wobble slightly. This wobble results in a periodic shift in the star's spectral lines, known as the Doppler shift. By measuring these shifts over time, astronomers can determine the planet's orbital period, mass, and distance from the star. The radial velocity method is highly sensitive to the mass of the planet, making it an excellent tool for detecting massive planets. However, it is less effective for detecting smaller, Earth-like planets, as their gravitational influence on the star is minimal. One of the primary advantages of the radial velocity method is its ability to detect planets around stars of various types and ages. Unlike the transit method, which requires the planet to pass in front of its star from our perspective, the radial velocity method can detect planets regardless of their orbital inclination. This makes it a versatile tool for exoplanet detection. Additionally, the method provides direct measurements of the planet's mass, which is crucial for understanding its composition and potential habitability. Despite these advantages, the radial velocity method has its limitations. It is less effective for detecting planets with long orbital periods, as the observational time required to detect a single wobble can be extensive. Furthermore, the method is sensitive to stellar activity, such as sunspots and flares, which can mimic the signals of orbiting planets. To mitigate these limitations, astronomers often combine the radial velocity method with other detection techniques, such as the transit method. The Kepler mission, for instance, has used both methods to confirm the existence of numerous exoplanets. By cross-referencing data from different detection methods, scientists can obtain a more comprehensive understanding of the exoplanet's properties. The radial velocity method continues to be a vital tool in the search for exoplanets, providing valuable insights into the diversity and distribution of planetary systems beyond our own. Ongoing advancements in spectrograph technology promise to enhance the method's sensitivity, enabling the detection of smaller, more Earth-like planets in the future. Radial velocity method, advantages and limitations. The radial velocity method, also known as the Doppler method, is a technique used to detect exoplanets by observing the gravitational influence they have on their host stars. This method relies on the fact that a planet's gravity causes its star to wobble slightly as the planet orbits it. Astronomers can detect these wobbles by measuring the shifts in the star's spectral lines, which are caused by the Doppler effect. The high-accuracy radial velocity planet searcher, HARPS, spectrograph, for instance, has been instrumental in discovering numerous exoplanets using this method. One of the primary advantages of the radial velocity method is its sensitivity to planets with relatively short orbital periods. This makes it particularly effective for detecting planets that are close to their host stars, including those within the habitable zone. Additionally, this method can provide information about a planet's mass and orbital characteristics. The method's ability to detect planets around relatively faint stars also makes it a valuable tool for exoplanet research. For example, the Kepler mission has used radial velocity measurements to confirm the existence of many exoplanets. However, the radial velocity method has its limitations. It is less effective for detecting planets with long orbital periods, as these planets cause smaller and slower wobbles in their host stars. This makes it challenging to detect planets in the outer regions of a star system. Furthermore, the method is biased towards detecting massive planets, as their gravitational influence is more pronounced. This can lead to an overrepresentation of gas giants in the detected exoplanet population. Additionally, the method requires high-precision instruments and long observation times, which can be resource-intensive. Another limitation is that the radial velocity method provides only the minimum mass of a planet, not its true mass. This is because the method measures the component of the star's velocity along the line of sight, which is influenced by the planet's orbital inclination. If the planet's orbit is inclined relative to our line of sight, the measured velocity shifts will be smaller, leading to an underestimation of the planet's mass. Despite these limitations, the radial velocity method remains a crucial tool in the field of exoplanet detection, often used in conjunction with other methods to confirm and characterize exoplanets. Direct imaging, fundamental concepts. Direct imaging stands out as one of the most intuitive methods for detecting exoplanets. It involves capturing actual images of planets orbiting distant stars. This technique relies on advanced telescopes equipped with coronagraphs, which block out the blinding light of the host star, allowing the much fainter light reflected by the planet to be detected. The process begins with selecting a target star known or suspected to host a planetary system. The telescope, often space-based like the Hubble Space Telescope or the James Webb Space Telescope, then focuses on this star. The coronagraph within the telescope's optics obscures the star's light, creating an artificial eclipse. This enables the imaging system to detect the dim light from any orbiting planets. The data collected is then processed to enhance the visibility of the planets, often revealing their position, brightness, and sometimes even their spectral characteristics. One of the primary advantages of direct imaging is the wealth of information it provides. Unlike indirect methods, which infer the presence of a planet through its effects on the host star, direct imaging allows astronomers to study the planet's atmosphere, composition, and even potential surface features. This method is particularly effective for detecting young, massive planets that are still hot from their formation and thus emit more infrared light. For instance, the Gemini Planet Imager has successfully imaged several such planets, including 51 Eridani b, a Jupiter-like planet located about 100 light-years from Earth. However, direct imaging faces significant limitations. The technique is challenging due to the immense brightness difference between a star and its planets. Additionally, it is most effective for planets that are far from their host stars, making it less suitable for detecting Earth-like planets in the habitable zone. To overcome these challenges, astronomers employ sophisticated techniques such as adaptive optics to correct for atmospheric distortions and specialized instruments to enhance contrast. Missions like the Sphere instrument on the Very Large Telescope and the upcoming Roman Space Telescope aim to push the boundaries of direct imaging. These advancements hold promise for detecting and characterizing more exoplanets, including those that might harbor life. Despite its limitations, direct imaging remains a crucial tool in the exoplanet hunter's arsenal, offering unique insights into the diversity and nature of planetary systems beyond our own. Direct imaging, coronagraphy, and adaptive optics. Direct imaging stands out as a method that aims to capture actual pictures of exoplanets, rather than inferring their presence through other means. This technique is particularly challenging due to the overwhelming brightness of stars compared to their orbiting planets. Two key technologies that enable direct imaging are coronagraphy and adaptive optics. Coronagraphy involves using a mask within a telescope to block out the light from the star, allowing the much fainter light from the planet to be detected. Adaptive optics corrects for the distortions caused by Earth's atmosphere, providing sharper images. The Gemini Planet Imager, for instance, uses both these technologies to image exoplanets. One of its notable discoveries is the planet 51 Eridani b, a Jupiter-like planet located about 100 light-years away. The advantages of direct imaging are substantial. It allows for the study of planets' atmospheres, compositions, and even weather patterns. By analyzing the light from the planet, scientists can determine its chemical makeup and potentially identify biosignatures, which are indicators of life. However, this method has its limitations. It is most effective for planets that are large, young, and far from their host stars, as these are the easiest to separate from the star's glare. Additionally, direct imaging is less effective for planets orbiting stars that are very close to Earth, as the star's brightness overwhelms the planet's light. The James Webb Space Telescope, with its advanced coronagraphs, aims to overcome some of these challenges by providing unprecedented sensitivity and resolution. In practice, direct imaging involves a series of steps. First, the telescope captures an image of the star system. Then, the coronagraph blocks out the star's light, revealing any nearby planets. Adaptive optics refine the image, enhancing its clarity. Finally, scientists analyze the data to confirm the presence of a planet and study its characteristics. The Subaru Telescope's HISEO camera has successfully used this method to image planets like GJ504b, a gas giant with a mass about 4 times that of Jupiter. Despite its promise, direct imaging remains a complex and resource-intensive process. It requires advanced technology and significant observation time, making it less efficient for detecting the vast number of exoplanets compared to other methods like the transit or radial velocity techniques. Nonetheless, it provides unique insights that other methods cannot, making it an invaluable tool in the search for exoplanets. Direct imaging, advantages and limitations. Direct imaging stands out as one of the most intuitive methods for detecting exoplanets. It involves capturing actual images of planets orbiting other stars. This technique is particularly valuable for studying young, hot planets that are still glowing from the heat of their formation. The most significant advantage of direct imaging is the wealth of data it provides. By directly observing an exoplanet, scientists can analyze its spectrum, which reveals information about its atmosphere, composition, and even potential signs of life. Additionally, direct imaging allows for the study of a planet's orbit, rotation, and weather patterns. Notable missions and instruments that have successfully employed direct imaging include the Gemini Planet Imager, the SPHERE instrument on the Very Large Telescope, and the James Webb Space Telescope, which is expected to revolutionize this field. However, direct imaging comes with substantial limitations. The primary challenge is the overwhelming brightness of the host star, which can obscure the much fainter light reflected by the planet. To overcome this, advanced coronagraphs and star shades are used to block out the star's light. Another limitation is the requirement for large telescopes with high-resolution cameras, which are expensive and technically demanding. Furthermore, direct imaging is most effective for planets that are far from their host stars, as the angular separation makes it easier to distinguish the planet from the star's glare. This means that Earth-like planets in the habitable zone of Sun-like stars are currently beyond the reach of this method. Despite these challenges, ongoing advancements in technology and techniques continue to push the boundaries of what direct imaging can achieve. In practice, direct imaging complements other exoplanet detection methods by providing unique insights that are not accessible through indirect techniques. For instance, while the transit method excels at detecting small, close-in planets, direct imaging is better suited for studying the atmospheres of larger, more distant planets. This synergy allows astronomers to build a more comprehensive understanding of the diverse range of exoplanets that exist in our galaxy. As technology advances, the capabilities of direct imaging are expected to improve, potentially enabling the detection and characterization of smaller, Earth-like planets in the future. Until then, it remains a crucial tool in the astronomer's arsenal, offering a direct window into the worlds beyond our solar system. Gravitational microlensing. Fundamental concepts. Gravitational microlensing is a fascinating phenomenon that occurs when the gravitational field of a foreground star acts as a lens, magnifying the light from a background star. This effect is due to the bending of space-time caused by the foreground star's mass, as predicted by Einstein's theory of general relativity. When a planet orbits the foreground star, it can cause additional brightening or dimming of the background star's light, revealing the presence of the exoplanet. The key to this method lies in the precise measurement of these brightness variations over time. The process begins with the alignment of a foreground star, known as the lens, and a background star, the source. As the lens passes in front of the source, its gravitational field bends the light from the source, creating a temporary brightening. If a planet orbits the lens star, it can cause a secondary brightening event, distinct from the primary event caused by the star itself. This secondary event provides crucial information about the planet's mass, distance, and orbital parameters. The observations in microlensing with K2, OMK2, campaign, for instance, utilize data from the Kepler Space Telescope to detect exoplanets using this method. One of the primary advantages of gravitational microlensing is its sensitivity to planets at large distances from their host stars, including those in the habitable zone. Unlike other methods, it does not rely on the light from the host star, making it particularly effective for detecting planets around faint or distant stars. However, the method has limitations. Microlensing events are rare and unpredictable, requiring continuous monitoring of large areas of the sky. Additionally, the interpretation of microlensing data can be complex, often requiring sophisticated modeling techniques. Despite these challenges, missions like the upcoming Nancy Grace Roman Space Telescope aim to leverage microlensing to discover thousands of exoplanets, furthering our understanding of planetary systems beyond our own. In practice, Gravitational microlensing complements other exoplanet detection methods by providing unique insights into planetary systems that might otherwise go undetected. For example, it can reveal planets with wide orbits that transit methods might miss. The method's ability to detect low-mass planets, including those in the Earth mass range, makes it invaluable for studying the demographics of exoplanets. However, the transient nature of microlensing events means that follow-up observations are often challenging. Researchers must act quickly to capture the fleeting brightening caused by a planet, making coordinated efforts between ground-based and space-based telescopes essential. Despite these hurdles, gravitational microlensing remains a powerful tool in the exoplanet hunter's arsenal, offering a glimpse into the diverse array of planetary systems that populate our galaxy. Gravitational microlensing, light amplification, and event analysis. Gravitational microlensing is a fascinating method for detecting exoplanets, relying on the bending of light due to gravity, as predicted by Einstein's theory of general relativity. This phenomenon occurs when a foreground star, known as the lens, passes in front of a background star, the source. The lens's gravity bends and magnifies the source's light, creating a temporary brightening event. If a planet orbits the lens star, it can cause additional, distinctive brightening patterns. The OGLE, optical gravitational lensing experiment, and MOA, microlensing observations in astrophysics, projects are prominent examples of missions employing this technique. They continuously monitor hundreds of millions of stars in the Milky Way's bulge, searching for these characteristic brightening events. The analysis of microlensing events involves measuring the change in the source star's brightness over time. A typical light curve, or graph of brightness versus time, shows a symmetric peak when only the lens star is involved. However, the presence of a planet introduces asymmetries or additional peaks. The shape and duration of these anomalies provide crucial information about the planet's mass, distance from its host star, and sometimes even its orbital parameters. For instance, the discovery of OGLE 2005 BLG 390lb, one of the most distant exoplanets known, was made possible through microlensing. This planet, located about 21 light-years away, orbits its star at a distance similar to that of Earth from the Sun, highlighting the method's capability to detect planets in remote regions of the galaxy. One of the key advantages of gravitational microlensing is its sensitivity to planets in wide orbits and those with low masses, including Earth-like planets. Unlike other methods, it does not rely on the planet's proximity to its host star or the star's brightness, making it particularly useful for detecting cold, distant planets. Moreover, microlensing events are rare and unpredictable, occurring only when the lens and source stars align perfectly. This rarity means that each event is a unique opportunity for discovery. However, the method has its limitations. Microlensing events are typically one-time occurrences, making follow-up observations challenging. Additionally, the interpretation of light curves requires sophisticated modeling, and the derived planetary parameters often have significant uncertainties. Despite these challenges, gravitational microlensing has contributed significantly to the field of exoplanet research. It has helped detect planets in regions of the galaxy that are difficult to probe with other methods. For example, the discovery of MOA 2007 BLG 192lb, a super-Earth orbiting a brown dwarf, demonstrated the method's potential to uncover planets in unusual systems. Furthermore, ongoing and future surveys, such as the Nancy Grace Roman Space Telescope's planned microlensing survey, promise to expand our understanding of exoplanet demographics and distributions. By leveraging the natural amplification of light through gravitational lensing, scientists continue to push the boundaries of exoplanet detection, revealing the diverse and complex nature of planetary systems beyond our own. Gravitational microlensing, advantages and limitations. Gravitational microlensing is a fascinating method for detecting exoplanets, leveraging the gravitational field of a foreground star to magnify the light of a background star. This phenomenon occurs due to the bending of space-time caused by the foreground star's mass, which acts as a natural lens. When a planet orbits this foreground star, it can cause additional, distinct brightening events. The OGLE, optical gravitational lensing experiment, and MOA, microlensing observations in astrophysics projects are prime examples of missions that have successfully employed this technique. These projects continuously monitor millions of stars in the direction of the galactic bulge, waiting for these rare microlensing events. One of the key advantages of gravitational microlensing is its sensitivity to low-mass planets. Unlike other methods, which often struggle to detect smaller, Earth-sized planets, microlensing can reveal these elusive worlds. It is particularly effective at finding planets that are far from their host stars, in regions where other detection methods fall short. Additionally, microlensing can detect planets around stars that are much farther away than those typically studied by other techniques. This makes it a valuable tool for probing the demographics of planetary systems in the Milky Way. The Kepler mission, while primarily known for its transit method, has also benefited from microlensing data to complement its findings. However, gravitational microlensing is not without its limitations. The primary challenge is the rarity of microlensing events. These events are unpredictable and brief, lasting from a few hours to a few days. This unpredictability makes it difficult to follow up on potential planet detections with other methods. Moreover, microlensing events are singular. Once the alignment between the foreground and background stars changes, the event cannot be repeated. This means that detailed follow-up observations are often impossible. Additionally, the method is biased towards planets with specific orbital alignments, which can skew the statistical understanding of planetary systems. Another limitation is the difficulty in determining the exact properties of the detected planets and their host stars. While microlensing can reveal the planet's mass and distance from its star, it often struggles to provide precise measurements. This is because the method relies on the chance alignment of stars, which does not always provide enough data for detailed characterization. Despite these challenges, gravitational microlensing remains a crucial tool in the exoplanet hunter's arsenal. Its unique capabilities complement other detection methods, offering a more comprehensive understanding of the diverse planetary systems that populate our galaxy. Transit timing variations, TTV fundamental concepts. Transit timing variations, TTV, is a method used to detect and characterize exoplanets, building upon the more common transit method. The transit method involves observing the periodic dimming of a star's light as a planet passes in front of it. TTV takes this a step further by analyzing the precise timing of these transits. If a planet's transit occurs earlier or later than expected, it can indicate the gravitational influence of another nearby planet. This variation in timing is what gives TTV its name. The fundamental concept behind TTV is rooted in the gravitational interactions between planets in a system. When two or more planets orbit a star, they can exert gravitational forces on each other, causing slight changes in their orbital periods. These changes manifest as variations in the timing of their transits. By carefully measuring these timing variations, astronomers can infer the presence of additional planets, even if those planets do not transit the star themselves. This makes TTV a powerful tool for detecting non-transiting planets and studying the dynamics of multi-planet systems. One of the key advantages of TTV is its ability to detect planets that might otherwise go unnoticed. For example, the Kepler mission has used TTV to discover several exoplanets that do not transit their host stars but still influence the transits of other planets in the same system. This method has been instrumental in the discovery of Kepler 11, a system with 6 planets, where TTV measurements help confirm the presence of the outermost planet. Additionally, TTV can provide insights into the masses and orbital parameters of the planets involved, offering a more comprehensive understanding of the system's architecture. However, TTV is not without its limitations. The method requires extremely precise timing measurements, which can be challenging to obtain, especially for faint stars or systems with long orbital periods. Furthermore, TTV is most effective in systems with multiple planets, where the gravitational interactions are more pronounced. In systems with only one known transiting planet, TTV may not be applicable. Despite these challenges, TTV remains a valuable technique in the arsenal of exoplanet detection methods, complementing other techniques like radial velocity and direct imaging. Its ability to reveal hidden planets and unravel the complexities of planetary systems makes it an indispensable tool in the ongoing quest to understand the diversity of exoplanets. Transit timing variations, TTV detection and analysis. Transit timing variations, TTV, offer a nuanced method for detecting and analyzing exoplanets, building upon the foundational transit method. This technique hinges on the observation of slight deviations in the regular intervals between transits of an exoplanet as it passes in front of its host star. These variations can reveal the presence of additional planetary bodies in the system, as gravitational interactions cause perturbations in the orbital periods. The Kepler mission, renowned for its prolific exoplanet discoveries, has extensively utilized TTV analysis. By monitoring the transit times of planets within the same system, scientists can infer the existence of non-transiting planets, even those too small or distant to be detected through direct transit observations. This method has been instrumental in identifying multi-planetary systems, such as Kepler 11, where 6 planets orbit a single star. The detection process involves precise timing of transit events over extended periods. High-precision photometry, as provided by missions like Kepler and the Transiting Exoplanet Survey Satellite, TESS, is crucial for identifying these subtle timing variations. Once a transit is detected, the observed times are compared against a predicted ephemeris or orbital schedule. Deviations from the expected times indicate the presence of additional gravitational influences. For instance, the Kepler 36 system showcased significant TTVs, leading to the discovery of 2 planets with highly eccentric orbits. The advantages of TTV lie in its ability to detect planets that do not transit their host star, thereby expanding the scope of exoplanet detection beyond the limitations of the transit method alone. However, the method requires extensive observational data and sophisticated analytical techniques to distinguish true TTV signals from noise and other systematic effects. Analysis of TTVs involves complex modeling to interpret the observed variations. Scientists use dynamical models to simulate the gravitational interactions within a planetary system, comparing these simulations to the observed transit times. This process can yield detailed information about the masses, orbits, and dynamical states of the planets involved. For example, the Kepler 9 system demonstrated TTVs that were successfully modeled to reveal 2 Saturn-sized planets in resonant orbits. The method's sensitivity to gravitational perturbations makes it particularly effective for detecting low-mass planets and characterizing planetary system architectures. Despite its strengths, TTV analysis is limited by the need for high-precision data and the computational resources required for detailed modeling. Additionally, the method is most effective in systems with closely spaced planets, where gravitational interactions are more pronounced. In practice, TTV analysis complements other detection methods, such as radial velocity and direct imaging, by providing a more comprehensive understanding of exoplanetary systems. The synergy between these techniques enhances the accuracy of exoplanet characterization, offering insights into planetary formation and evolution. Missions like the upcoming Plato, planetary transits, and oscillations of stars are poised to further advance TTV studies by providing high-precision photometry over extended baselines. This will enable the detection of smaller planets and more subtle dynamical interactions, pushing the boundaries of exoplanet research. As observational technologies and analytical methods continue to evolve, TTV analysis will remain a vital tool in the quest to understand the diversity and complexity of exoplanetary systems. Transit timing variations, TTV advantages, and limitations. Exoplanet detection has evolved significantly, with various methods offering unique insights into these distant worlds. Transit timing variations, TTV, is one such method that has gained traction due to its ability to detect and characterize exoplanets, particularly in multi-planet systems. This technique builds upon the more common transit method, which observes the dimming of a star as a planet passes in front of it. TTV, however, focuses on the slight variations in the timing of these transits, which can reveal the presence of additional planets in the system. The advantages of TTV are manifold. It is highly sensitive to the presence of additional planets, even those that do not transit the star themselves. This makes it a powerful tool for detecting non-transiting planets in systems where at least one planet does transit. Moreover, TTV can provide detailed information about the masses and orbits of these additional planets. For instance, the Kepler mission has successfully used TTV to detect and characterize several exoplanets. One notable example is the Kepler 11 system, where TTV measurements revealed the presence of 6 planets, including some with masses and orbits that were previously unknown. This method is particularly useful for studying systems with closely spaced planets, as the gravitational interactions between them cause measurable variations in transit timing. However, TTV is not without its limitations. The method requires precise and frequent transit timing measurements, which can be challenging to obtain. Additionally, the variations in transit timing can be subtle, making them difficult to detect and interpret. This often necessitates long observation periods and sophisticated data analysis techniques. Furthermore, TTV is most effective in systems where at least one planet transits the star. In systems where no planets transit, TTV cannot be used. Despite these challenges, TTV remains a valuable tool in the exoplanet hunter's arsenal, complementing other methods and providing a more comprehensive understanding of exoplanetary systems. Another limitation of TTV is its sensitivity to noise and systematic errors. These can arise from various sources, including instrumental noise, stellar variability, and atmospheric disturbances. Such noise can obscure the subtle variations in transit timing, making it difficult to distinguish between true TTV signals and spurious ones. To mitigate this, researchers often employ advanced statistical techniques and data processing methods to filter out noise and isolate genuine TTV signals. Despite these efforts, the presence of noise and systematic errors remains a significant challenge for TTV measurements. Nonetheless, ongoing advancements in data analysis and observational techniques continue to enhance the capabilities of TTV, making it an increasingly powerful tool for exoplanet detection and characterization. Astrometry, fundamental concepts. Astrometry, a method that measures the precise movements of stars on the sky, offers a unique approach to exoplanet detection. At its core, astrometry works by tracking the tiny wobbles or shifts in a star's position caused by the gravitational influence of an orbiting planet. This technique is particularly sensitive to planets with long orbital periods and can detect planets that other methods might miss. The European Space Agency's Gaia mission, launched with a primary goal of creating the most accurate 3D map of the Milky Way, is also contributing valuable astrometric data that could reveal new exoplanets. The process begins with high-precision measurements of a star's position over time. Telescopes equipped with advanced detectors capture images of the star, and sophisticated software analyzes these images to detect even the slightest shifts. These shifts, often measured in microarc seconds, are then used to calculate the planet's mass and orbital characteristics. One of the key advantages of astrometry is its ability to detect planets at large distances from their host stars, including those in the habitable zone. However, this method requires extremely precise instruments and long observation times, making it challenging to implement from the ground. Despite its challenges, astrometry has shown promise in recent years. The HARPS mission, a precursor to Gaia, demonstrated the potential of astrometry by detecting the wobble of a star caused by an unseen companion. While HARPS did not confirm any exoplanet discoveries, it paved the way for future missions like Gaia, which is expected to detect thousands of new exoplanets using astrometric techniques. Ground-based efforts, such as those using the Very Large Telescope Interferometer, are also contributing to this field, albeit with more limited precision. The combination of space-based and ground-based astrometry is providing a more comprehensive view of the exoplanet population, complementing other detection methods like transits and radial velocity. Astrometry, precision measurement and data analysis. Astrometry, a method that measures the precise movements of stars on the sky, is one of the oldest techniques in astronomy. It's like watching a dance of stars, where the subtle wobbles can reveal the presence of an unseen partner, an exoplanet. This method is particularly sensitive to planets that are far from their host stars, something other methods struggle with. The European Space Agency's Gaia mission, launched with the primary goal of creating the most accurate 3D map of the Milky Way, is also sensitive to astrometric signals from exoplanets. It's a bit like trying to detect a firefly next to a lighthouse from a great distance, but with incredibly precise instruments. The process involves taking multiple images of a star over time and measuring its position with extreme precision. If a star has an orbiting planet, its center of mass will shift slightly due to the planet's gravitational influence. This causes the star to wobble, and astrometry can detect these tiny movements. The advantage of astrometry is its ability to detect planets in orbits far from their host stars, where other methods like transit or radial velocity struggle. However, it requires extremely precise measurements and is less sensitive to smaller planets closer to their stars. The data analysis involves complex algorithms to filter out noise and other stellar jitter, making it a computationally intensive process. In practice, astrometry is often used in conjunction with other methods to confirm planet detections. For instance, the Hubble Space Telescope has used astrometry to help confirm the existence of several exoplanets. The upcoming Nancy Grace Roman Space Telescope, with its wide field of view and high precision, is expected to significantly advance the field of astrometric exoplanet detection. Despite its challenges, astrometry offers a unique window into the dynamics of planetary systems, providing insights that complement other detection methods. It's a testament to the power of precision measurement in pushing the boundaries of our understanding of the universe. Astrometry, advantages and limitations. Astrometry, a method that measures the precise movements of stars on the sky, offers a unique approach to exoplanet detection. It works by tracking the tiny wobbles in a star's position caused by the gravitational influence of an orbiting planet. This technique is particularly sensitive to planets with long orbital periods and those far from their host stars. The European Space Agency's Gaia mission, launched with a primary goal of creating a three-dimensional map of our Milky Way, is also capable of astrometric exoplanet detection. Its unprecedented precision allows it to measure stellar positions with an accuracy of a few microarcseconds, making it a powerful tool for this purpose. One of the key advantages of astrometry is its ability to detect planets in orbits too wide or too long period to be easily found by other methods. It can also provide direct measurements of a planet's mass and orbital inclination, offering valuable insights into planetary systems. Additionally, astrometry is less sensitive to the brightness of the host star, making it useful for studying planets around faint or distant stars. However, this method has its limitations. The tiny movements it detects are often at the limit of current technological capabilities, requiring extremely precise instruments and long observation times. Moreover, astrometry is less sensitive to planets with short orbital periods, and it struggles to detect planets with masses much smaller than Jupiter's. Another challenge is that astrometric signals can be mimicked by other astrophysical phenomena, such as the presence of binary star systems or instrumental noise. This can lead to false positives, requiring follow-up observations to confirm planet candidates. Despite these limitations, astrometry plays a crucial role in the field of exoplanet detection, complementing other methods and providing unique insights into the architectures of planetary systems. As technology advances, the precision of astrometric measurements continues to improve, promising exciting discoveries in the future. The upcoming NASA mission, the Wide Field Infrared Survey Telescope, WFIRST, will also employ astrometry to study exoplanets, further highlighting the importance of this method. Combining multiple detection methods, the quest to discover exoplanets has led to the development of several sophisticated detection methods, each with its unique advantages and limitations. Combining these methods has proven to be a powerful approach, enhancing the accuracy and comprehensiveness of exoplanet detection. The transit method, for instance, involves measuring the dimming of a star's light as a planet passes in front of it. Missions like NASA's Kepler and TESS have successfully used this method to identify thousands of exoplanets. However, it has limitations, such as the requirement for the planet's orbit to be aligned edge-on with the line of sight from Earth. This method is particularly effective for detecting planets close to their stars, but it struggles with smaller, Earth-sized planets. Radial velocity, another prominent method, detects the wobble induced in a star's motion due to the gravitational pull of an orbiting planet. This technique has been instrumental in discovering many exoplanets, including those around nearby stars. The HARPS spectrograph, part of the ESO's Las Silla Observatory, is a prime example of a tool that excels in this method. Yet, radial velocity is less effective for detecting smaller planets and those with longer orbital periods. Combining transit and radial velocity methods can provide a more complete picture. For example, the transit method can identify potential candidates, while radial velocity can confirm their existence and provide mass estimates. This synergy allows astronomers to gather more detailed information about the exoplanets, including their size, mass, and orbital characteristics. Gravitational microlensing offers a different approach by observing the brightening of a background star's light as a foreground star with a planet passes in front of it. This method is particularly useful for detecting planets at greater distances from their stars, including those in the outer regions of stellar systems. The microlensing observations in astrophysics, MOA, and the optical gravitational lensing experiment, OGLE, are notable projects that have utilized this technique. However, microlensing events are rare and unpredictable, making this method less consistent than others. Despite this, when combined with transit or radial velocity data, microlensing can provide unique insights into the distribution and properties of exoplanets across different regions of the galaxy. Direct imaging, though challenging, involves capturing actual images of exoplanets by blocking out the light from their parent stars. This method is particularly effective for detecting young, massive planets that are still hot and bright. The Gemini Planet Imager and the Sphere instrument on the Very Large Telescope are examples of advanced tools designed for direct imaging. However, direct imaging is limited by the brightness of the parent star and the distance of the planet from it. Combining direct imaging with other methods can help confirm findings and provide additional data. For instance, direct imaging can offer visual confirmation of a planet detected through radial velocity or transit methods, enhancing the overall understanding of the exoplanet's characteristics. By integrating these diverse detection methods, astronomers can overcome individual limitations and gain a more comprehensive understanding of the exoplanets and their environments. Future prospects and emerging technologies. The quest to discover exoplanets has led to the development of sophisticated detection methods, each with its unique advantages and limitations. Transit photometry, one of the most successful techniques, involves measuring the dimming of a star's light as a planet passes in front of it. Missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, have utilized this method to great effect, identifying thousands of exoplanets. The primary advantage of transit photometry is its ability to detect small, Earth-sized planets. However, it requires precise alignment between the star, planet, and observer, limiting its scope. Additionally, it's more suited to detecting planets close to their stars, making it challenging to find those in the habitable zone of Sun-like stars. Radial velocity, or Doppler spectroscopy, measures the tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. This method has been instrumental in discovering many exoplanets, including those around nearby stars. The HARPS, High-Accuracy Radial Velocity Planet Searcher, spectrograph, for instance, has been highly successful in this regard. Radial velocity can detect planets regardless of their orbital alignment, and it provides information about the planet's mass. Yet, it's less sensitive to smaller, Earth-sized planets, and the presence of multiple planets can complicate the signal. Moreover, it's biased towards detecting planets close to their stars, similar to transit photometry. Direct imaging offers a more intuitive approach, capturing actual images of exoplanets. This method is particularly useful for studying young, massive planets orbiting far from their stars. The Gemini Planet Imager and the Sphere instrument on the Very Large Telescope are examples of advanced direct imaging systems. Direct imaging allows for the study of an exoplanet's atmosphere and composition. However, it's technically challenging due to the overwhelming brightness of the host star. It's also less effective for detecting smaller, Earth-like planets. Despite these limitations, advancements in adaptive optics and coronagraphs are improving the capabilities of direct imaging. Gravitational microlensing detects exoplanets by measuring the magnification of a background star's light as a foreground star passes in front of it. This method is sensitive to planets at large distances from their stars and can detect low-mass planets. The microlensing observations in astrophysics, MOA, and the optical gravitational lensing experiment, OGLE, are notable projects using this technique. Microlensing events are rare and unpredictable, making follow-up observations difficult. Additionally, it typically provides only a snapshot of the planet's properties, without the possibility of further study. Nevertheless, microlensing complements other methods by probing different regions of planetary systems. Future prospects in exoplanet detection are bright, with emerging technologies promising to overcome current limitations. Star shades, or external occulters, are space-based structures that block starlight, enabling direct imaging of exoplanets. The Roman Space Telescope's coronagraph instrument will use a similar principle to study exoplanets. These technologies aim to capture images of Earth-like planets and analyze their atmospheres for biosignatures. Additionally, advancements in spectrographs and detectors are enhancing the sensitivity and precision of radial velocity and transit methods. The James Webb Space Telescope, with its advanced infrared capabilities, will enable detailed studies of exoplanet atmospheres and compositions. Moreover, space-based interferometry, which combines light from multiple telescopes to achieve higher resolution, is being explored for exoplanet detection. Missions like the proposed Large Interferometer for Exoplanets aim to use this technique to directly image and characterize Earth-like planets. Advances in data analysis and machine learning are also expected to improve the efficiency and accuracy of exoplanet detection methods. These emerging technologies and approaches hold the potential to revolutionize our understanding of exoplanets and the possibility of life beyond our solar system. Comparative analysis of detection methods. The quest to discover exoplanets has led to the development of several innovative detection methods, each with its unique advantages and limitations. The transit method, one of the most prolific, involves measuring the dimming of a star's light as a planet passes in front of it. This technique is highly effective for detecting planets with short orbital periods and has been instrumental in the discoveries made by missions like NASA's Kepler and TESS. The Kepler mission, for instance, has identified thousands of exoplanet candidates using this method. However, the transit method has its limitations. It is biased towards detecting planets with orbits that are edge-on from our perspective, and it struggles to detect planets around faint or distant stars. Another powerful method is the radial velocity technique, which detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. This method is particularly good at finding massive planets close to their stars. The high-accuracy radial velocity planet searcher, HARPS spectrograph, for example, has used this technique to discover numerous exoplanets. Yet, it has its drawbacks. It is less sensitive to smaller, Earth-like planets and can be affected by stellar activity, such as sunspots and flares. Moreover, it requires high-precision instruments and long observation times, making it resource-intensive. Gravitational microlensing offers a different approach. It relies on the gravitational field of a foreground star to act as a lens, magnifying the light from a background star. If a planet orbits the foreground star, it can cause a detectable anomaly in the magnification. This method is unique because it can detect planets at large distances from their stars and is sensitive to low-mass planets. The microlensing observations in astrophysics, MOA, and the optical gravitational lensing experiment, OGLE, are notable projects using this technique. However, microlensing events are rare and unpredictable, making this method less consistent than others. Additionally, it typically provides only one-time measurements, making it challenging to study individual planets in detail. Direct imaging, while challenging, offers the advantage of capturing actual images of exoplanets. This method involves blocking out the light from the parent star to reveal the much fainter light from the planet. The Gemini Planet Imager and the Sphere instrument on the Very Large Telescope are examples of advanced instruments using this technique. Direct imaging is particularly useful for studying the atmospheres of young, massive planets. Nevertheless, It is limited by the brightness of the parent star and the distance of the planet from its star. It is also less effective for detecting Earth-like planets, which are typically too small and too close to their stars to be imaged directly. Each method has its strengths and weaknesses, and the choice of method often depends on the specific goals of the observation campaign. Impact of exoplanet detection on astrophysics and planetary science. The quest to find exoplanets, those elusive worlds beyond our solar system, has revolutionized our understanding of the cosmos. One of the primary methods for detecting these distant planets is the transit method. This technique involves observing the slight dimming of a star's light as a planet passes in front of it. The Kepler Space Telescope, launched by NASA, is a prime example of a mission that has successfully employed this method. It has discovered thousands of exoplanets by monitoring the brightness of over 150 zero stars. The advantages of the transit method include its ability to detect small, Earth-sized planets and provide information about the planet's size and orbit. However, it has limitations. It requires the planet to pass directly between the star and the observer, which is a rare alignment. Additionally, it is more suited to detecting planets close to their stars, making it challenging to find those in the habitable zone of Sun-like stars. Another fascinating method is the radial velocity technique, also known as the Doppler method. This approach measures the tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. The High-Accuracy Radial Velocity Planet Searcher, HARPS, spectrograph, part of the European Southern Observatory's La Silla Observatory, has been instrumental in this method. It can detect planets as small as Earth, but it is more effective for planets close to their stars. The radial velocity method has the advantage of providing information about the planet's mass and orbit. Yet, it is less sensitive to small planets and those far from their stars. Moreover, it can be affected by the star's own activity, such as sunspots and convection, which can mimic the signals of planets. Gravitational microlensing offers a unique way to detect exoplanets. This method relies on the gravitational field of a foreground star acting as a lens, magnifying the light from a background star. If the foreground star has a planet, the planet's gravitational field can also affect the light, creating a distinctive signal. The microlensing observations in astrophysics, MOA, and the optical gravitational lensing experiment, OGLE, are notable projects using this technique. Microlensing can detect planets at large distances from their stars, and even rogue planets not bound to any star. However, it has limitations. The events are rare and unpredictable, making follow-up observations difficult. Additionally, microlensing provides limited information about the planet's orbit and usually only detects the planet once. The impact of exoplanet detection on astrophysics and planetary science has been profound. It has challenged our understanding of planet formation and solar system architecture. The discovery of hot Jupiters, massive planets orbiting very close to their stars, was a significant surprise. These findings have led to new theories about planetary migration and the dynamics of young solar systems. Moreover, the study of exoplanet atmospheres has provided insights into the chemistry and potential habitability of these distant worlds. Missions like the Hubble Space Telescope and the upcoming James Webb Space Telescope have been crucial in this endeavor. They have detected molecules like water, methane, and carbon dioxide in exoplanet atmospheres, offering clues about their environments. The field of exoplanet research continues to evolve, with each new discovery adding a piece to the puzzle of our place in the universe. As we've journeyed through the cosmos of exoplanet detection methods, we've seen how the transit method, with its dips in starlight, has been brilliantly employed by missions like Kepler and TESS to uncover thousands of distant worlds. We've explored the radial velocity method, which uses the wobble of stars to reveal the presence of unseen planets, a technique championed by instruments like HARPS. We've marveled at the precision of direct imaging, which captures actual photos of exoplanets, though it's limited to large, distant planets, as seen in the work of the Gemini Planet Imager. And we've delved into the gravitational microlensing method, which uses the bending of light to detect exoplanets, a technique that has led to discoveries like those made by the MOA and OGLE collaborations. The advantages and limitations of each method paint a vivid picture of the challenges and triumphs in our quest to understand the universe beyond our solar system. Each method brings us closer to answering the age-old question, are we alone in the universe? As you continue to gaze at the night sky, remember that every star could be a sun, and every sun could be a host to worlds beyond our imagination. The search for exoplanets is not just a scientific endeavor. It's a journey of discovery that connects us all. So, keep looking up, keep wondering, and join us in our next cosmic adventure as we dive deeper into the mysteries of the universe. Subscribe and hit the bell icon to stay updated on our latest explorations. Together, let's reach for the stars.